Good afternoon. With
Shenderov will give a talk now. Guys.
hello, good afternoon. We have lots of ground to cover and not a lot of time. So as you can see, the talk is titled Homo Exploratoris, and what on earth could be Homo Exploratoris? Well, here's an example. This is James Irvin, Apollo 15 lunar module pilot in this photo. That's the species that he belonged to. Mars was clearly the next destination on Homo Exploratoris itinerary, and everybody knew that. It was a beautiful idea, an inspiring one, and for a time, widely popular. But then we discovered apparently much more important things for our scientists and engineers to be busy themselves with. And for 70 years, the dream of becoming a multiplanetary species has been shattered so many times that it's time to, ask a reasonable question: what went wrong? Now, a lot of us at this conference, including yours truly, are engineers, and asking this question is part of what we're trained to do for a living. It's called failure analysis. And the point of the exercise is to find how we prevent similar failures in the future. And that's what I'm going to attempt to do in the next 25 minutes. It is tempting to focus on the technical challenges, and there is absolutely no shortage of those, starting with the rocket, which is a tower of many millions of parts, built by the lowest bidder and loaded with enough explosive to flatten a small town. If it blew up, which is exactly what they were doing in the early 60s, way too frequently to inspire any confidence. On May 25th, 61, when JFK pitched the idea of going to the moon to Congress, the US didn't have a working rocket to take humans to Leo, farthest the moon. So to the decision makers in Congress, the idea of going to the moon must have looked like a really bad case of biting off more than we could chew. And still they went for it. And the prevalent explanation of why they went for it is, of course, the space flight of Yuri Gagarin 6 weeks prior. Vostok K, whose first flight carried Gagarin to orbit, had 25% failure rate and no crew escape system. Mercury Redstone also took John Glenn to space on his fourth launch, and the first of the four was a failure, and the crew escape system, which Mercury Redstone actually did have, was one of the things that didn't work. So the level of risk acceptable to Gagarin and Glenn and to outfits they flew for was obviously quite high. Saturn V, that eventually flew to the moon, was designed using slide rules, manufactured using technology of 1960s, and yet when it flew to space 13 times, it never once failed. Of course, lacking a time machine, no one could know that in May 1961. American leadership just chose irrationally, without any data, to believe that we can do it. And in 1969, we did. Rationally, the hardware to put people on Mars and the plan to do it, and most importantly, the organizations capable of pulling it off, were for the most part available in 1969. When Saturn V, with Saturn V's 0% failure rate, the Mars mission was likely flyable one way or another based on that hardware. Steely-eyed missile men would have gladly flown. 53 years later, we have resources no one could dream of back then. The total price tag of Apollo program was 46% of US GDP in 61 when it was adopted, 20% in 72 when it was abandoned, and 1.1% of last year's GDP. We can afford stuff we couldn't afford back then. Elon Musk could almost single-handedly actually buy us a full program, which is almost what he's doing. The government didn't get any poorer either. The 2021 US government budget was 8 times bigger than it was in 1961. We also have very useful things too that we didn't have. We have composites and alloys, computers and sensors, simulation software and control systems, lightweight nuclear reactors and solar panels that are available today are something that von Braun and Korolev would have gladly traded their right hands for. Quoting Dr. Zubrin, we are much better prepared to send humans to Mars today than they were to get men to the moon in 1961. Yet they got there in 8 years. We've gone nowhere in the past 3.5 decades. It's over 5 decades now. So rational reasons for why we haven't gone to Mars yet are not very convincing. Is the problem irrational then? Is it all in our imagination? What failure analysis typically focuses on is objective, measurable, and rational. It is clear, however, that we're not going to Mars without first choosing to do it. Once we have made that choice, whether to pursue the challenging goal very, very rational, in a very rational way, if we have to any shot of getting there. But lacking a time machine, the goal itself cannot be set rationally. We don't know how it's going to turn out. As Yogi Berra once said, it's hard to make predictions, especially about the future. There was no way to know beforehand the return on investment in Columbus expedition, or in the Apollo program, or in James Webb Telescope. When you don't know what you're missing, you cannot put a price on it. Risk-taking can't be rationally justified, not without a time machine to deliver data from the future for making a choice today. Our irrationality, by the way, is not an alternative for rationality. That's a very common mistake. It is not an alternative to rationality. It's the only way available to us humans without an oracle to choose what to be rational about. Encyclopedia Astronautica has a whole story about Mars expeditions that never happened. And they have a very important statement in there. No compelling concept emerged. The key point there, the key word there is compelling. Compelling who? These folks who are building Empire State Building in 1932 without any belay whatsoever. These folks who are walking over the polar ice to check if a huge axle is actually sticking out of North Pole and see that for themselves, or folks who need this kind of warning stuck on their baby strollers. Because these different groups of people would have very different requirements for what they find compelling. Now, clearly, human perception, in particular human perception of themselves, self-image, is very relevant to the issue of going to Mars. And it's anything but objective and rational. This picture is a very abbreviated codex of all our biases. Well, actually, quite a few of our biases. I never list them all. There's no way of listing them all. And some biases are more pronounced in you, some others in me. That's why we're individuals. So each of us look at the same world through a different filter set. The biases are our individual filter sets. Some biases, though, are more common in some societies, and one of them is negativity bias. See that one with red arrow? That's the one. Why is it important? Well, negativity bias is people's refusal to believe that the world is getting better. Humanity is the most numerous, prosperous, knowledgeable, healthy, and peaceful it's ever been, but a lot of fools aren't buying it. And negativity bias is an inexhaustible source of convenient rationalizations to take no risks, which going to Mars is full of. Risk-averse people don't find escaping the Earth's gravity well and going to Mars compelling. Citizens of countries with most citizens of countries with most resources to invest in such an ambitious enterprise tend to be more risk averse and therefore less likely to approve of their governments or their business people to embark on such an adventure. Actually, yes, China appears to be the world champion as far as the percentage of people who think that world is getting better. Why? Well, because they kind of see it. You know, they live in a developing country, and developing means that it is getting better on a time scale noticeable by naked human eye. That's what we have. So risk-averse people go nowhere. And using up resources while going nowhere is certainly a bad idea. As Peter Thiel once told Mark Zuckerberg, the biggest risk you can take is not taking any risks. Neanderthals, for example, being a bit too rational for their own good, never escape the Malthusian trap where they lived for 400,000 years. As soon as a competition more willing to bet on themselves, that would be grandpa and grandma around, Neanderthals went the way disposable rockets are going right now. Malthusian trap is a situation when everybody competes for the same finite resource. And the idea is that you cannot have infinite growth based on finite resource as long as you take no risk of going elsewhere and looking for a superior replacement. And for most of human history, that's where we lived. We lived for most of human history in the Malthusian trap. But by the time Thomas Malthus was born, we actually no longer lived in the trap. What got us out was human ingenuity. And the way that works is creative people don't wait for a resource to be exhausted. They find a replacement long before they run out. Like this. We didn't go to using coal because we ran out of dung or firewood. We didn't go to oil and gas because we ran out of coal. We found a new resource and we found it better than what we were using, and that's where we switched. Now, let's consider a couple of interesting resources, and I'm not talking about Martian resources, I'm talking about terrestrial ones. You can't make humans or human food for that matter without water and phosphorus. Believe me, I got PhD in cell biology. You can't make humans without water and phosphorus. Naturally, when something is that important, what you go after first is the low-hanging fruit, the easiest resource to find. That's guano on an island. Same with water. We first go to rivers, then shallow freshwater aquifers, and this plot shows the average depth of a freshwater well in California. It went up fivefold from 1940 to 2005, from 100 feet to 500. So it takes a lot more energy to get water that we cannot live without and phosphorus that we cannot live without than it used to. But maybe that's not the problem, because the energy at our disposal actually is going up. And since the beginning of Industrial Revolution, that's the phosphorus. Since the beginning of Industrial Revolution, energy at our disposal has been doubling every 25 years. So that sounds very optimistic. Unfortunately, with energy, we also went after the low-hanging fruit first. So the concept of EROI, energy return on energy investment, is basically how much of the energy contained in a barrel of oil did you use to extract that barrel. And 100 years ago, it was 100. Today, it's 10. Okay, when it gets to 1, all the energy contained in a barrel of oil will be used for extracting that barrel of oil. Was nothing left for any running human civilization. Now, do we have better alternatives? Well, we have alternatives, but we better scale them up in the remaining 47 years. Otherwise, our fate will have very little to do with going anywhere. And I don't mean Mars. So this is the time plot of what the energy has been doing lately. And if you extrapolate that to the time where on the time axis, you have this red mark for where we'll run out of oil, meaning we won't run out of oil. Just won't be any point in digging it up anymore. Okay, it's 75% of our energy at that time will still be derived from oil, meaning that instead of going up in energy in that 50 years twice, fourfold up, we're going fourfold down. If we do business as usual, if we continue investing our resources in scaling up energy alternatives the way we're doing right now, we are, instead of going fourfold up, we're going fourfold down. Now, going exponentially up in energy is what's been envisioned as humanity's future. And this is the famous Kardashev scale of civilizations. Type 1 is the civilization that controls the energy that its home star sends to its home planet. Type 2 controls all energy of its home star, and type 3 controls all energy of its entire galaxy. Just as a reference point, if we continued doubling every 25 years, we would have reached type 1 in 300 years, type 2 in 900 more years, and type 3 in 900 more years. So exponential function is a real nice thing if it goes up and you want it to go up. And vice versa, of course. You lose momentum, and before you know it, you're rolling backwards. Like Elon Musk once told Dr. Zubrin, if we don't see something close to exponential improvement in our rate of innovation, we will not reach Mars. I think that if we don't see exponential improvement in our rate of innovation, we will not keep our terrestrial civilization for long either. Accelerating growth is the only way we know how to run this civilization. We never had a decelerating humanity of 8 billion people. We don't know how to run it. We never tried. We don't even have any concepts. There will be obviously need to skip over quite a few things. So yes. Why do I think that we are important? Well, being human, it helps my ego to think so. But in reality, what happens is space is a shooting gallery, and in shooting gallery, every life-bearing planet will be sterilized one day or another, one way or another, unless it does something interesting, which is to evolve a civilization that climbs production scale and learns to use its resources to save itself, to save its biosphere, and to plant backup copies of it elsewhere in case protection fails. Okay, so we never run out of selective pressure. That's how evolution works. This is our selective pressure. And what does it select for us? It selects for us because we are now learning. With Dart experiment, we just demonstrated that we are learning to do what every self-respecting civilization is supposed to learn to do: protect itself and its biosphere from cosmic catastrophes. Well, the humanist hypothesis is that intelligent civilization forming life is an evolutionary adaptation. The civilization protects itself, its biosphere, from catastrophes, and it plants backup copies itself elsewhere in case it fails. And as civilization matures, it learns to protect itself and its home biosphere from more rare, more destructive events. And no, we're not doing great, but I think I've told you that, so we can skip over this. This is how confident we can make ourselves based on scarce data of anything we choose to convince ourselves of. And that is peak humanity, which is our most important resource. And humans are apparently choosing not to make more humans anymore, and that is seriously concerning. That is what we're supposed to see ourselves is if we were to choose to make more of ourselves, of our biosphere, and so on and so forth, and not this and not that. This is a little history, and this is what we are doing right now, and that's what we're supposed to be doing. All right. Now, the big picture, and that's the book I wrote about it, titled the same as this talk, and notice the subtitle: Is Humanity an Apprentice God? Okay, that is the last thing I'm going to talk about, and that is If you zoom out to the next step, from humanity protecting this planet of ours that has an expiration date, so does our entire universe. Unless, again, it produces some civilization that, again, climbs all the levels of Kardashev scale and learns to make universes at will. And then the universe immortalizes itself the same way we do, having kids, the same way our biosphere can, having kids with our help. Well, maybe our universe can do exactly the same thing. Have kids via a couple of interesting mechanisms that could be mediated by us. And actually, Dr. Zubrin has done quite a bit of original research on how it can be done via black holes, which is a technology we need. That's hopefully what we're going to be doing. If Mars Society convinces everybody, or at least a critical mass of everybody that we should. Thank you.
So I think one of the most disturbing parts of that energy chart that you showed us was not so much the slope of the line, including renewables, but the fact that nuclear power is in fact shrinking, even though that's the only viable alternative to fossil fuels. That's consistent. What is your opinion about that, and how do you think that should be dealt with?
Well, I think we have plenty of options. One very obvious option that we don't need any technology development for is based on the fact that we live on a ball, half of which at any given time is illuminated with sunlight. So if we choose to sell energy to each other in the same way we're selling everything else, which is global, okay, we won't need any new technology because we know how to build power lines and we know how to make solar panels. That's all we need, as long as we can learn in time to trust ourselves to sell each other energy. Whoever is on the illuminated side is the seller, whoever is on the dark side is the buyer. The challenge here is that the folks who suggested that idea first in 1915, in 2015, were Chinese. And that formed a very strong and persistent opposition to this idea, not on its merits, but on its origin. I hope that this can be overcome, because this is the easiest technologically option for us to do, and the cheapest, right? The other one is of course nuclear with thorium, mostly with thorium, and the problem with thorium is again political, because most of thorium, everybody who is interested in thorium knows is in India. And when India blew up their nuclear bomb, they were excluded from all the nuclear collaborations, and all the Indian nuclear scientists and all the Indian nuclear related politicians remember that, and they hold their resource and their technology and everything else dear and near to their heart, and they may not be in the mood to really share all of that. They've been doing quite a bit of work, but only folks that they're seriously cooperating with on thorium are the Chinese, and even there, for again political reasons, it's one.
Thank you, Alex.